G'day. In this video, we're going to have a look at a new factorizing technique called completing the square. Now, before I start doing that, I should just let you know that this will be a slightly longer video than usual because there are some concepts we need to get across. I'll go through some basic examples in this video, and then in subsequent videos, we'll look at some more complex examples. Now, quadratic trinomials are trinomials, usually with an x, but it doesn't have to be x, but trinomials where you've got a variable squared with a coefficient in front, even if that coefficient is 1. And then we've got the variable by itself, usually with a coefficient, even though b might be 1, and then a constant term, c. So ax squared plus bx plus c is what we call a quadratic trinomial, or it could be at squared plus bt plus c, or whatever else. A, b, and c are numbers. A and b are any number other than, or a is any number other than 0. B and c could be any number including 0. So a quadratic nomial could be, examples could be like 3x squared is an example, 3x squared plus 1 is an example, 4x squared plus 2x minus 7 is an example, and so on. So all of these are kinds of examples of quadratic trinomials. Now, the next point is not when a quadratic trinomial is useful. We'll go through that in a different video. But in terms of this particular technique of completing the square, I think once we've gone through it, you'll probably think it's a lot of work for not much gain, potentially, when we've got other factorizing techniques. But I just wanted to say that it is quite a useful skill to pick up, because it becomes really useful when we look at quadratic functions. So that means things like graphing a trinomial, like y equals 3x squared plus 2x plus 1. We're graphing it, for example, or we're trying to find solutions. So like 3x squared plus 2x plus 1 equals 0, and we need to find the values of x for which that is true. All of those kinds of things are when completing the square is actually quite a handy tool. So bear with me as I go through how to use it, and know that it will make more sense in subsequent topics or parts of topics. In terms of the general form, what it looks like after we've completed the square, it's going to look like something like this. This could be just 1, but something a multiplied by, and then inside we've got an x minus h squared. And that's just a general form. It could be, if h was negative, for example, then that would be an x plus h. And then we've got a value outside, and that value could be 0, so it might not be there, but it kind of is, if you know what I mean. So for example, after completing the square, it might look like this, or it might just look like this, and technically it could even look like this, although that's just a square, isn't it, really? But still technically it could be done. Okay, I'm just going to zoom out so you can see all the examples at once now, and we're going to go through each of these examples in turn, and I think it's the best way to explain the process. Now, the first thing I wanted to point out is that this particular example here, example 1, is something that you should have seen before, and you should be getting to the point that you can recognize what this is. I'll give you a moment to pause the video and think through how you would factorize that, and then I'll come back to you. Okay, so I just wanted to point out that there's a squared term here, and then the giveaway is that 25 is also a square term. So if I was spelling it out a little bit, I'd probably just point out that that is 5 squared, and that this is 2 times 5 times x. And so we have an x here from the x squared, we have the 5 here from the 5 squared, and we have double it in the middle as well. So it fits the pattern of a perfect square. So we can say that is equal to, just to put it in black, that is equal to x plus 5 all squared. In a similar way, if I had x squared minus 10x plus 25, Then again, this bit here tells us it's a 5 squared. This bit here is 2 times 5 times x, and so this factorizes to x minus 5 all squared based on our perfect square patterns. Okay, so that's just a reminder. That's what perfect squares are. That the x term, not the x squared term, is basically 2 times x times whatever the constant term is squared. Okay, so let's have a look at example 2. We don't have a perfect square here, do we? We've got an x squared here, we've got a 10x here, and we've got a 24 here. Okay, so we would need that to be 25 in order for it to be a perfect square. So this is where the cheat comes in. What I can do is I can write down x squared plus 10x plus 24, and I need 1 to turn it into 25, but I can't just add 1 to an expression and keep it the same. So I then subtract 1, and that effectively removes it again. But now I'm just being selective with my additions here, like so. And now I'm going to take this bit and I'm going to turn it into a perfect square. So you can see that knowing your patterns and how to apply the rules directly rather than factorizing longhand is really important here. So the bit inside brackets simply becomes x plus 5 all squared minus 1. And I just wanted to point out that this is now in this format. A is equal to 1, h is equal to negative 5, minus 5 is plus 5, and k is equal to negative 1. So it is in that form, and almost always it's absolutely fine to leave it in. In terms of when you'd want to use completing the square, this is the form you basically want to get, and then we do things with it from there. But I just wanted to point out something else, and it's okay if you don't quite get this, that this is actually, at this point, also a difference of 2 squares. So I would have x plus 5 minus 1 multiplied by x plus 5 plus 1, which is equal to x plus 4 multiplied by x plus 6. So I would call this format here partially factorized. We've factorized a bit of it, and I'd call this fully factorized, which is useful as well for other reasons. So there you go. Now, we're going to have a look at, on slide 20 there, we're going to have a look at example 3, and I'm going to start off with exactly the same equation, or expression, I should say, and this time I'm going to give you a different method, and this method is the one I would probably encourage you most strongly to use across all completing the square problems. So what we're going to do is we're going to basically have a look at the bit that I'm just putting a little blue bracket around there, the x squared plus 10x. And what we're going to do is we're going to just go straight to putting in a bracket, and because I've got an x term here, I'm going to put an x here. Because I've got a plus here, I'm going to put a plus here. And then I'm going to close the bracket. Oh, so I'm not going to close the bracket yet. And then I'm going to put in the following thing. I'll say it and then I'll write it a little bit later just for the board notes. I'm going to look at the coefficient of the x term, that's 10, and I'm going to halve it. That gives me 5. Then I'm going to close my bracket and put the square in. Then straight away, I'm going to subtract 5 squared. Okay, the 5 that I just worked out and the square there. So I'm going to take away the 25, and then I'll put the plus 24 at the end as it was. When I simplify that, I get x plus 5 all squared. Minus 25 plus 24 isn't still with a minus 1. And now I'm at the same point as I was over here. And I could fully factorize it from there. So it gets me to the same point, but just a little bit process driven rather than having to think about what that final square term looks like. So I strongly encourage you to do it. Now, just to break it down a little bit, just so you've got some thinking behind it, what we're doing here is we're going, that middle term has to be, if I've got a plus b all squared, then that's a squared plus 2ab plus b squared. So the middle term is 2 times by a number times by the other number. Now, in quadratic trinomials, then a is always x effectively. And so you've got 2 times what times x. And if you have a look here, 10 is 2 times what times x. So that's basically 10 there. And so the what is going to have to be 5. And I effectively do that by dividing 10 by 2. And it will always be divided by 2 because that's how the perfect square expansion works. So you're always taking the coefficient of the middle term or the x term and dividing it by 2 to get your b term. Okay, so that is basically it for my examples. In the next video, I'll go through some different examples. So for example, what happens if this is a subtraction here? What happens if this is an odd number? And what happens if a is bigger than 1 effectively here? So a non-monic quadratic. So we'll do those in the next video and see how you go with these ones.